This is a lesson that typically is a kind of 2-day lesson, okay? There are 5 examples here that we're going to go through today, but we are not going to solve or finish any of the 5. We're going to set up equations for all 5 of them, and your homework will be to solve the equations to get answers to the problems, okay? So we're dealing here with word problems that end up, when you set them up, turning into rational equations. So there's a word problem on assignment number 5 that I've given you, which is due tomorrow. I'm going to say I'll take that assignment in Friday because I really want you focusing, once we're done with this lesson, on completing these questions, okay? So I will take your assignment number 5 in Friday. Let's get started. There are 5 specific examples here, and I would say that each of the 5 illustrate a specific type of question that you would expect to see on an exam, whether it's a unit exam or a final exam, or maybe a quiz or an assignment. So example 1 talks about painting a room, and if we have a particular room, maybe it's in a hotel and you have all of these rooms that are the same, and you hire Stella to paint the room. It takes her 4 hours. And the room right next to Stella's room where she's painting, Jose paints an identical room, but it only takes him 3 hours because he's more experienced. Okay? The question then becomes, if they go to a third room which is identical and they paint together, how quickly can they paint the room? How many hours is it going to take? And this is a difficult question, and tomorrow I will show you a shortcut to it. But what some people believe, and with a bit of thought you can see that it's not going to make sense, is you just average those times. Right? I mean, that's a strategy that you might think is valuable, but what's the average of 3 and 4? Well, 3.5 hours. That doesn't make any sense, because Jose can paint the room in only 3 hours. So why should it take longer if Stella's helping out? So what we're going to be doing in order to solve this is we're going to be looking at a rate. A rate at which a job is done is always measured with respect to time. Okay? So, for example, the rate at which I spend money during the month would be so many dollars per day. The rate at which I eat chicken wings on Friday night would be so many chicken wings per hour. The rate at which I use electrical energy, and it's indicated on my electrical bill, would be so many kilowatts per day. They might use different units, but the point is a rate is always measured relative to time. And if we take a look at the rate for Stella, Stella has a rate of 1 room per 4 hours. That's the rate at which she can paint. She can paint a room every 4 hours. And if you take a look, so this is Stella, if you take a look at Jose, Jose can paint a room, 1 room, in 3 hours. And you know, the bottom line is a rate is found by taking the number of the things divided by the time. So if over a course of a 3-hour chicken wing binge on a Friday night, I ate 40 chicken wings, then you would take 40 chicken wings divided by 3 hours. And what I would get, other than a whole bunch of shame, would be whatever 40 over 3 is, and it would be chicken wings per hour. Okay? Well, we don't have 40 divided by 3, but we do have 1 divided by 4, so I can write the rate here for Stella as 0.25 rooms per hour. And this should start to make sense to you. Because if she can do a whole room in 4 hours, then in 1 hour she's only doing a quarter of a room. Unfortunately, if we take 1 divided by 3, we get this. And it's a repeating decimal, which is awkward to work with, algebraically speaking. So we're going to rewrite this as 1/4 of a room per hour and 1/3 of a room per hour. And I'm perfectly aware, I think, that many of you might even question why I bother to write 0.25. Because 1 over 4 is a quarter, okay? But these are the rates. Okay, so that's the first little mini lesson to this question. The second lesson is the following. So let's just, I guess that's the answer. We'll get to that later. Let's just park that idea of these rates and Stella's rate and Jose's rate on the side. Let's talk about, I'm not going to say 3 hours. I'm going to say 1.5 hours. Okay, for my chicken wing binge. Okay, and I'm going to say that I ate 60 chicken wings in 1.5 hours. Okay, I'm a mess. Okay, covered in sauce. My lips are all burning. What does that work out to? Can you work out what that is? I think it's 40. Is it? 40 chicken wings per hour. Okay, let's say that I was a machine. I was a chicken wing eating machine, and I never varied from that rate. I always ate at a continual steady rate 40 chicken wings per hour. Okay? And next weekend comes around. I've been eating salad all week. Next weekend comes around. You go, Mr. Way, what are you doing? I'm going to go eat chicken wings. Really? How many are you going to eat? Well, I don't know, but I'm going to sit there for 5 hours and eat chicken wings. Okay? The question is, if it was 40 wings per hour, how would I use that and the 5 hours to find out how many wings I would eat? Well, I would multiply, wouldn't I? You'd go 40 wings per hour times 5 hours. And the hours cancel and you're left with 200 wings. So what am I talking about here? I'm talking about the quantity always being equal to the rate times the time. The quantity is always the rate times the time. Always. And that could be chicken wings per hour. It could be, remember I used as an analogy that I spend so much money per day. Let's say I was spending $122 per day on average in a month. If I said to you, and that's a rate, if I said to you, how much money will I spend over 12 days, then you take the rate times the time. This is an important mathematical idea. Rate times time gives you the amount. Kilometers per hour times hours gives you kilometers. Okay, what that means, going back to this problem, is that the rate at which Stella works multiplied by the time she works will give you how many rooms she paints. Okay? 1/4 times the time will be how many rooms Stella paints. If Stella painted, and let's just try something here. If Stella painted for 12 hours, and you put 12 here, 1/4 times 12 is 3. You're going to really have to settle down and think in your brain here. She paints 1 room in 4 hours. Doesn't it make sense that in 12 hours she would paint 3? Okay. So we take the rate times the time. Jose, if we take Jose's rate, which is 1/3 times the time he paints, this is how many rooms he will paint. How many rooms do we want them to paint together? 1. Well, these two amounts have to give you 1. They have to give you 1. Now, again, tomorrow I'm going to show you a very neat shortcut to solving this kind of problem. I would caution you, and maybe it's just me, but the method explained in the textbook is confusing to me. And it could be that it's just confusing to me, but I would rather teach something to you that I have a very high level of understanding of. It's not confusing. And that way I can do a better job teaching you than trying to force feed you something that I don't quite get. The way the textbook does it is a little weird in my mind. This is the equation you have to solve for tomorrow. The equation is t over 4 plus t over 3 is equal to 1. It is a rational equation, okay? We're not solving it right now. That's part of your homework. And this is a type of word problem in this unit that you need to know how to do. Let's take a look at number 2. Number 2 is a relatively simple problem to set up. It says the sum of two numbers is 30 and the sum of the reciprocals is 5 over 36. What are the numbers? Well, we have to start off by defining the numbers. X is going to be one number. What will the other number be? Christy, do you know?
I don't know if it's right, x plus 2. I don't know.
This is not a case, I know why you're saying x plus 2. This is not a case like the assignment where we have two consecutive even numbers, where one number would be x and the other would be x plus 2. So that would work if I said two consecutive odd or two consecutive even numbers. Paige? It would be 30 minus x because they have to add up to 30. Right? I mean, if I tell you that between you and I we have $30, and you say, well, how much money do you have? And I go, well, I got $5. If we have 30 in total, then you must have 25. You must have 30 minus the 5. And now we build the equation. It says the sum of the reciprocals, well, the reciprocal is 1 over. A sum is plus. The sum of the reciprocals is 5 over 36. This is a very simple equation to set up once you've seen it. And there could be similar types of questions, like maybe the sum of the two numbers is 40, in which case it would be x and 40 minus x. So this is the equation that you are going to have to solve for x. And I'm not going to give you the answer to this one. I'm just going to say when you find x and then you take 30 minus it to get the other number, take the reciprocals of them and add them together and see if you get 5 over 36. And if you do, you've done it right. Number 3, maybe the most important kind of question. Whenever you have, well, there's an exception. The final example in today's lesson is going to look like something that fits into this category, but it doesn't. Whenever you have two different trips, and it could be a train that's going fast between two cities and the train going slow between the two cities. Or it could be me walking to the store and then me running back because I realized I forgot to turn off my oven. I don't know. It doesn't matter. It could be I'm in Wetaskiwin and Alva is in High River, and we are going to meet, her and I, in Sylvan Lake. So I drive from Wetaskiwin to Sylvan Lake, and Alva drives from High River to Sylvan Lake. There's two trips. Could be different people, could be the same people. You always set these up by building a table in which across the top you have speed, distance, and time, and across the side you have the two trips. So if I was solving a problem in which it was Alva and I meeting in some central location, I would put Alva here and Paul. If it were me walking to the store and then running back home, I would put walking and running. Here, what do we have? A train has a run of 170 kilometers from one city to the next, someplace in Saskatchewan. And it talks about if the regular speed is decreased by a certain amount, then it's going to take a certain length of time more. What's the regular speed? Okay. So we're going to have regular speed, and slower. Smaller speed, slower train. Now, I mean, you have to try to memorize something here. You have 3 columns to fill in, and the first column is always filled in the same way. Sometimes it will be the speed column, sometimes it will be the distance column, sometimes it will be the time column. It's filled in because you know the values. Someplace in this question, you're told the speeds or the distances or the times. They're not unknown. And it says it's 170 kilometers. So we put that in first. If you were told in a different question the actual speeds of the trains, then you would put them in first, because maybe then you'd be trying to find the distance. The second column that you fill in is filled in based on what you're trying to find. Let's cut to the chase. What are you asked? What is the regular speed? So we start filling in that column. If you want to know what the regular speed is, then you're going to have to call that an unknown. You're going to have to call it x. But we still haven't filled in the rest of this column. Okay, we have not filled in the rest of this column. I want everybody to think about this. If the regular speed is x, then what am I going to put for the slower speed? How many of you have an idea of what I can put for the slower speed?
X minus 16.
X minus 16. We're almost there. We're almost to the equation. But this last step is the most work. The third column is filled in by asking yourself what you do to the other 2 columns to get the third column. So I'm saying, what is it you do with distance and speed to get time? And I admit this is almost a science thing, but speed, you should know, is distance over time. If I multiply both sides of this by t, which strangely enough, this is a rational equation. It's got a denominator. If I multiply both sides by t, I get distance equals speed times time. I'll use s for speed. You can use v for speed if you like. And don't forget, what I'm telling you is the third column is found by filling in what you do with the other 2 columns to get the third column. And distance divided by speed gives you time. And I would probably say, I really hope, that most of you know the time is the distance divided by the speed. And I mean, I just know that because if I want to travel 500 kilometers at 100 kilometers per hour, it's going to take me 5 hours. 500 divided by 100 is 5. So that means that this is 170 over x, and this is 170 over x minus 16. It's distance divided by speed. And for the most part, everybody, we're done for the most part. We're done with everything except for what's in red. Everything else in this chart was designed to get us to the red point. And now we build an equation using these 2 times. Okay? Imagine that I told you in a question, forget about this question, imagine that I told you that the time it took me to get to Sylvan Lake and the time it took Alva to get to Sylvan Lake was the same. Then we could just set these 2 red things equal to each other. But these are not the same, right? So I'm going to write these down. And there's something that's very slippery here for a lot of students. I'm going to write down 170 over x and 170 over x minus 16. I'm going to leave a bit of room there. And my question to you is, reading the question carefully, or looking at those expressions, which of those is a bigger number? I'm asking you, is the thing on the left bigger than the thing on the right, or is the thing on the right bigger than the thing on the left? And the answer, you may need to look at what's missing from the screen here, which is what the question is saying. How many of you are pretty confident you know which of those is bigger? Okay, so put up your hand if the left side is bigger. Put up your hand if the right side is bigger. It's the right side. This is tricky. This is tricky. It's not obvious. Excuse me for a second. So one of the ways to look at this is that the slower speed is connected to the time 170 over x minus 16. But if I'm driving really slow, right? I want to drive from here to Edmonton, and I have some mechanical issues with my truck, and it's just plugging along at 20 kilometers per hour. The slower I'm driving, the longer it takes me to get there. So this is bigger. Now, you can also determine that this is bigger, because if I take 170 divided by x, and then I divide by something smaller than x, I'll get a bigger result. Okay? Now, the reason I'm saying that, and the reason we're after which is bigger, is because if I were to do this right now, this is not a valid equation, because the right-hand side is bigger. It's like a teeter-totter. The right-hand side is on the ground. In order for me to balance it, which is what an equation is, I have to add more weight to the side on the left. And the mathematical weight is a half hour. It takes a half hour more. And, you know, trust me, I've been doing this enough to know this is confusing. Because I'd be willing to bet even the best students, many of the best students, when you say the run takes a half an hour longer when you're going slower, I guarantee you people want to write plus a half over here. They do. It just makes sense. Oh, it takes a half hour more. But what this is saying is that this 170 over x minus 16 equals a half hour more than the other time. So this is the equation that you're going to have to solve. And I'm pretty sure that what's going to happen is you're going to get a quadratic equation, and it's probably not going to be factorable. Okay? All right, number 4 is a classic kind of problem. I'm trying to hit the classics here. I'm trying to hit the 5 questions that you would likely see on an exam. A group of students are going to go on a trip. And the trip costs $4,200. And it costs $4,200 no matter how many students go. That's it. It's a flat rate. If more students decide to go, it's still $4,200. Which would mean if more students decided to go, they would each pay less if they're going to share the price equally. But imagine that we all decided to go on a trip. $4,200, you go, can I afford it? And I take 33 plus myself, which is, well, we'll just go students because teachers ride for free, okay? 33 students. What's 4,200 divided by 33? 100 and something. I don't know. Have you got it, Nate? 127.3. Okay, so about $127 to $128. And imagine that all of these people decided, you know what, they weren't going to go. What are these people going to feel? Well, they're going to feel the pinch because their price is going to go up. If all of a sudden I go from 33 people down to 20 people, then instead of paying $127 and something, you're going to end up paying $210 per person. So that's what's going on here. They're going to share the price equally, but 8 students decide not to go. All of the extra students, all of the students who are still going to go, have to pay $12.50 more. So how many students go on the trip? Well, let's call N the number who go. Often in your textbook they would say n is the number who planned on going. Since you're asked how many actually go, I would go with n as the number who actually go. Well, what that would mean is that 4,200 divided by n is how much each of those students pay. Fair enough? How many were going to go? N plus 8, which means 4,200 over n plus 8 is how much they were going to pay per person. These two things are not equal, right? One of them's bigger. Which is bigger? I think if I don't go through this thought process with you of which is bigger, students, really good students, put that 1250 on the wrong side of the equation quite often. So just slow down when you get to this point. Which is bigger? Left side or the right side? It's going to be the left side. Because when fewer people go, you pay more. And don't be frustrated by that, because I can see the frustration in some of your faces, because I saw some people going, oh no, it's the right side, and they were confident. And now their hearts are broken because I'm telling them it's the left side. Another way to look at it is the denominator of this is a bigger number. So if you divide something by a bigger number, you get a smaller result. And that might be the way that some of you want to go in these questions. I'm just taking the approach that if fewer people go, you pay more. That means that these two things are not in balance. The one on the left is more. Okay? And as a teeter-totter-ish kind of example, it's like that right now. And in order for us to balance things out, we have to add that 1250 to the other side. And when I do, well, I'm going to, in keeping with what we're talking about here, write this as 25 over 2, because we are talking about rational expressions. And now we can say they are equal. And there's the equation that you would need to solve. If this turns into a quadratic equation that has two solutions, the quadratic equation must be factorable, because the number of students is a number of students. It's not kind of part of a student. And the other thing I will mention is that if it is quadratic and you get two n's, one would be a negative n, which wouldn't count. That's the equation you need to solve for tomorrow. And we have one more to go. So we've done 4. We're going to do one more, leaving you probably about 10 to 15 minutes to get started on solving these equations. So you're going to have 5 equations to solve for homework. And I'm saying it's homework. I need you to get them done. How many of you have taken Physics 20? How many of you are taking Physics 20 right now? Okay. Must be offered right now then. If you've taken Physics 20, this will be a lot easier to understand. 2 canoers are in a river and they can paddle at 6 meters per second. I want to stop and explain the physics of what that means. It means that if I put my canoe in a swimming pool, a big Olympic-sized swimming pool, and we start paddling, we're going to push the water back at 6 meters per second, which means the canoe, if you're standing there watching us, the canoe will be drifting by at 6 meters per second. 6 meters per second is pretty fast, so drifting is maybe the wrong word. Okay? Imagine now, though, that I've got an Olympic-sized swimming pool on this gargantuan cruise ship. And the cruise ship is traveling that way at 5 meters per second. Okay? So I'm going to draw this from the top down. We have this cruise ship. I know. My artistic abilities are baffling. And there's a pool on the cruise ship. And the cruise ship is moving this way at 5 meters per second. And here's the canoe. Ish. and the canoe is moving this way at 6 meters per second. If you're watching the canoe from this chair on the deck of the ship, the canoe will be moving at 6 meters per second, won't it? But if you're sitting on the shore here, that canoe is going to be moving at 11 meters per second. Because the whole ship is moving at 5 meters per second, and in the ship, I'm moving at 6 meters per second, so it's going to be passing you by at 11. It would be like a walkway, one of those long walkways at the airport. You know what I'm talking about? And the walkway is moving that way at 5 meters per second, and there's a spider on the walkway, a very athletic spider that can move that way at 6 meters per second. And you're standing off of the walkway and you're watching the spider. It's going to be flying by you at 11. Now, what if we get to the end of this and I canoe backwards? Well, not backwards. From my perspective, I canoe paddle at 6 meters per second to the left. How fast will I be moving relative to a person on the boat? Well, 6 meters per second. How fast will I be moving relative to this person? 1 meter per second. You know, and if I did this, it would be a very strange thing to watch. You can try to wrap your head around it. The boat would be moving, but the canoe would be staying in the same spot relative to the person on the shore. It would be kind of an interesting thing to watch. Well, rather than having a cruise ship, what we have is a river. So when I say that I travel against the current, my speed against the current will be slower than my speed with the current. How many of you recognize from Physics 20 this kind of analogy? I mean, I didn't use that analogy, but this idea that you have the speed being increased or decreased depending on the water. Remember those types of problems? Okay. So we can paddle at 6 meters per second. Let's just, don't write this down because it's not in the question. If the river was flowing at 3 meters per second, better not use 3, at 2 meters per second, then this would be 4 and this would be 8. Just run that through your head. That if I was paddling at 6 meters per second in a river that's flowing at 2 meters per second and I was paddling with the water, then relative to the shore I'd be moving at 8. You've maybe seen movies where people are paddling, or video clips where people are paddling in a river that's moving very fast. They're hardly paddling at all, but they're really moving. Okay. The point I want to make is that this speed will be 6 minus the speed of the river, and this speed will be 6 plus the speed of the river. So this little v is the speed of the river. So what do? They travel 6.75 kilometers upstream, stop for lunch, return downstream, and then we have a comparison of times. Well, we're going to set up a table. There's the answer, by the way. We're going to go, I'll say slow and fast, speed, distance, and time. And we're going to fill in one of the columns with numbers. Is there something we know? What is it? Do we know the speed? Do we know the time? What do we know? It's the distance, right? 6.75 kilometers. 6.75 kilometers there, 6.75 kilometers back. But I'm going to use 6,750 because I want to work in meters because the speed that we have to work with is in meters per second. You can't use kilometers and meters in the same equation. We can put for the slow speed 6 minus v, and for the big 6 plus v. The fast speed. By the way, listen very carefully, we can stop and handle this right now. The big speed will give us the small time, right? The faster you go, the smaller the time. The time is distance over speed. This is just like the previous question we did. So 6750 over 6 minus v, and 6750 over 6 plus v. And I'm going to write those two down. We know these times are different. In fact, we're told how different they are. 10 minutes less. So where do I have to add the 10 minutes to make this equal? I have to add it to the smaller one. That's right. I just saw somebody mouth smaller one. I have to add it to the smaller one, which is the one on the right.